Welcome to Empowered Learning. This is the second video in the video series on improper integrals. So in the first video, we went over a lot of the basics for improper integrals, which meant we first studied what a proper integral was and compared that to what an improper integral would be. Then we looked at improper integrals in terms of the type classifications that they are. Type 1 improper integrals and type 2 improper integrals. So just as a summary for that, a type 1 improper integral is one where the upper or lower limits are not a real number, and thus because of that we have a situation where our actual integrand could possibly have a horizontal asymptote in the graph of that function, or we have a situation where the integrand as x approaches positive or negative infinity could itself go to positive or negative infinity. Okay? A type 2 type of integral, improper integral, is one where your integrand is probably going to have either a jump discontinuity in it or a vertical asymptote that is within the limits of integration that you're talking about, or let's say at the end values of your limit of integration you have that vertical asymptote or other type of discontinuity, sometimes jump discontinuity. Okay, so the kind of categorize them very simple. Type 1 type integrals normally have horizontal asymptotes in it, but not always. Type 2 integrals are normally going to have vertical asymptotes or some other type of jump discontinuity in it. Okay, and of course with both of those, the limits of integration in and of themselves, one of them could not be a real number, or both of them could not be a real number. Okay. So the purpose of this video is to get some more practice in being able to identify improper integrals. But specifically to start off, we want to figure out, hey, is an improper integral that we are looking at, can it converge or not? Okay. If it converges, that means we could work it out, and we could work it out and get a real number value for it. Or if there are no by hand techniques to do it, if we use, let's say, numerical integration or use a computer or whatever, it would actually be able to work it out for us. If the improper integral is divergent, then what that means is no matter how we try to work it out, we're not going to get an answer for it. So it's either going to go to, let's say, positive infinity, negative infinity, or it will be like a does not exist type case. Okay. All right, so for this first example here, we have an improper integral, and we know that mainly because of the fact that our upper limit here is going to infinity. Okay. Now, we see here that for our actual integrand itself, f of z, which is just this 1 over z squared plus 3z plus 2, we see that if we factor this out this way, that we have vertical asymptotes at z equals -1 and 2, and thus the fact that 2 is in between 0 and infinity is another reason why this particular improper integral here is improper. Okay, so by definition here, because this has this should be a -2. Sorry, that should be a -2. And so because of that, yeah, so this will end up being a type 1. Because those vertical asymptotes are not within this interval of x values here. So this would be a type 1a. Okay? Yeah, sorry about that. All right, so from here we know that once we have this in this form, we could use partial fraction expansion to be able to break this up in a way to where we can actually take the antiderivative of this integrand here. If you're not familiar with partial fraction expansion, I'm going to encourage you to please look at my videos on partial fraction expansion, as they'll explain the technique that I'm using here to get the values of a and b to shorten the process of being able to evaluate this improper integral. So using the shortcut technique for finding a and b for partial fraction expansion of linear non-repeating factors, then we see that a ends up being 1, b ends up being a -1 here, and then we just use that to be able to complete everything. So our function f of z can be rewritten in this way, and we go ahead and by definition of what an improper integral is, we do the limit as b approaches infinity of the definite integral of our newly rewritten version of f of z from 0 to b. And so from here, I'm not going to go through all the gory details in detail, but you see that we can take the antiderivative of both of these terms relatively easy, and then from here we go ahead and evaluate at the upper limit minus the lower limit, and then of course from here we see that all this just is going to simplify into something that looks like this. And I'm rewriting it that way because I know that I'm going to have to evaluate the limit of this particular result. And so to me, it's easier to look at the limit in this result versus this one or this one. Okay? So once we do that, we evaluate the limit, what we see here, and of course, everywhere where we see b, we're plugging in infinity. And we know that any real number divided by infinity in terms of limits goes to 0. And after all that's being said and done, we see that this first term here ends up going to 0. Second term is just natural log of 2. And since the natural log of 2 is a real number, this lets me know that not only does this improper integral converge, meaning that we actually end up getting a, we can actually find the answer for it. In this case, the actual answer is natural log of 2. So if we wanted to translate that, the area under the curve of our given function 1 over z squared plus 3z plus 2 from 0 to infinity, if we were to actually calculate the area under the curve of that, it would total out to be a value of natural log of 2 square units. Okay, so that's what this means here. All right, so for our next example here, I'm just going to go ahead and say up front that this is going to diverge. Okay, now the reason that it diverges, if we kind of use common sense here, it'll make a whole lot of sense to us. We have cosine of pi x. Okay, so cosine of pi x in general is going to look like a cosine function, and it's going to bounce up and down like this, and I'm just going to do it for 2 periods. And since this is pi, then we know that full period is going to happen within 2 units, okay, which means half a period's here at 1 unit. So here, the fact that this cosine function just keeps going and going, it's going to keep oscillating back and forth in between -1 to 1, from negative infinity to positive infinity. There is no way for us to actually be able to calculate the area under the curve of that particular function, because it's just going to keep, the area is just going to keep getting bigger and bigger and bigger the more cosine of pi x extends out as x approaches negative infinity and positive infinity. Okay, so just using common sense here and knowing what the graph of what cosine of pi x looks like, you know that it's going to diverge. Now, all this work I've done here is for those that can't necessarily accept that, then I computationally show you that it's not going to converge. Okay, and so here, because I have cosine going from negative infinity to positive infinity, this is going to be a type 1c type of function. So I break it up into 2 separate improper integrals. Basically a type 1b here and a type 1a here. Okay? And so, of course, you see that if I try to find out what is the value of this improper integral for the first one, which I've called I1, you see I've taken the antiderivative of cosine of pi x, which is sine of pi x divided by pi, evaluate that from a to 0, and notice that I get to the point here that I end up having to figure out what is a sine of negative infinity. And of course, we don't really know what that is. Okay, so because we don't know what sine of negative infinity is, because again, infinity is not a real number, it's a concept, then we're kind of stuck and we can't really evaluate that at all. So just that alone lets you know that this particular integral is going to be convergent, because I1 is going to be, let me say that again. We know that this particular improper integral here is going to be divergent because I1 is divergent. Okay, and it's all because of this issue that we have here. Okay, now we could do the same thing with the second term, but there's no need to, because since the first term is divergent, then that means that automatically the whole entire improper integral is divergent. So for that reason, we know here that this particular improper integral is definitely going to be divergent because of that. All right, so now let's do a problem from scratch here. And again, it's the same thing. We want to know whether this particular improper integral is going to be convergent or divergent. If it is convergent, we want to try to find what its actual value would end up being here. Okay, so the first thing that I want to state here, so that we're not confused, is that this particular integral is not of this type. Okay, it is not of this type. Notice the difference here. Okay, remember that this special case type of improper integral here only works if the upper limit here is infinity. Okay, since this is 1, I can't equate it to what I'm doing here. So because of that, I'm going to have to I can't look at this and say, well, since the value of p here is going to be less than 1, meaning that if I was to write this way, I could look at it like this. I can't say that because p is 1/5, which is less than 1, that this particular improper integral is going to diverge. Okay, can't say that. Okay, so I'm actually going to have to go through the process of actually evaluating this particular improper integral here to see if it actually does converge or not. All right, so now that we know what we can't consider, now let's actually try to evaluate this particular improper integral. Okay, now note that this integral is improper because of the fact that I can rewrite this way. I want to rewrite it like this. And that this integrand here, the 1 over x minus 1, all that raised to 1/5, it does have a vertical asymptote here at x equals 1, which is the exact same value as the upper limit of my definite integral here. Okay, so we know because of that, this is going to be an improper integral, because I basically have a discontinuity at the upper limit. Now, for us to work this out, we would do it as if we were in a normal first-year calculus course. I see that it would be easy for me to evaluate the antiderivative of x raised to the negative 1/5, but not x minus 1 raised to the negative 1/5. So what I want to do is do u substitution. So I'll let u equal x minus 1, and if I take the derivative of u with respect to x, that's just going to be du over dx is just going to be equal to 1. And that means that du is equal to dx. Okay. So therefore, we know that if I was to look at this way, then my integrand would just simply be u raised to the minus 1/5 now. Okay. For my limits of integration, I know that I can rewrite everything in terms of u now. So let's say if I do u of 0, and of course 0 is an x value, so 0 minus 1 is just going to be a negative 1, and u of 1 is just going to be 0. So this now will be negative 1 to 0. And remember, du is equal to dx, so that would just be du. And so now we have our integral in the form that we need to have it in, make life easy for ourselves. And here we can just take the antiderivative of u raised to the minus 1/5. So that would end up being u raised to the 4/5 times 5 over 4. And we'll evaluate this part of it from negative 1 to 0. Okay. Now, in doing this, notice that I'm forgetting something. And what I'm forgetting here is the fact that this 1 that is right here that got replaced with a 0 is still a vertical asymptote here at u equals 0. So in me doing what I'm doing here, if I just go and plug in, let's say, 0 right here, this is not going to work out well. Okay. So what I need to do to correct this, according to the definition, is I need to write this more formal so that we can actually see what's going on. So here, what I would need to do is do limit as, let's say b, well, let's say t in this case. Yeah, I think I'll keep it simple and just do b. So let's say b approaches 0. And since it's the upper limit, we're going to be approaching this from the left of integral from negative 1 to b of u raised to the minus 1/5 du. Okay, so this tells us that, well, we recognize that our upper limit is actually a place where we have a discontinuity, and what we need to do is, of course, evaluate that to see what's going on. Okay, so we're going to evaluate the improper integral in terms of b, and then take the limit of that to see what the final answer ends up being. So we do this, and of course the limit as b approaches 0 from the left is just going to stay there. And now all that stuff that we did earlier, we'll go ahead and evaluate that. So in other words, find the antiderivative of u raised to the negative 1/5. So if we do that, then of course it's going to be 5 over 4 u raised to the 4 over 5. And that's going to be evaluated from negative 1 to 0. And let's get this tightened up here. Negative 1 to 0. And let's change the way that this looks so that we have a difference. Okay. So limit as b approaches 0 from the left. And now we're going to plug in 0 in for u. It's going to be 5, fourths, 0 raised to the 4 fifths, minus 5 fourths, negative 1 raised to the 4 fifths. Of course, here we know that this first term, all of that will end up going to 0. So what this will end up being now is minus 5 over 4 times the fifth root of negative 1 raised to the 4. All right, so here we know that negative 1 raised to the positive 4 is 1, and the fifth root of 1 is 1. So all of this is just 1. And so what this ends up just being here at the end of the day is just going to be a negative 5 over 4. Because, of course, if we take the limit of any constant, it's just going to be that constant. So we see that this ends up being the answer. And since this is a real number, then we know that this particular integral, improper integral, will indeed converge. And the actual area under the curve value, if you want to call it that, is going to be a negative 5 over 4. And of course, the negative just means that we have net more area that is below the x-axis than it is above. Okay. So to kind of finalize everything here for this problem, we'll say therefore the integral from 0 to 1 of x minus 1 raised to the minus 1/5 dx is going to be equal to a negative 5/4, which means that this integral converges. Okay. All right, so let's move on to the next example. So for this next example, I wanted to throw one in here that involve trigonometric functions, just so that you can see that we do have some trig functions to where the integrals actually end up being improper because of the vertical asymptotes that arise in some of our reciprocal trig functions. And of course, we know that cosecant is the reciprocal of sine. And so because of that, we're going to have vertical asymptotes at all integer multiples of pi. Okay? And notice that we're asked to find out essentially the area under the curve of this secant function from pi over 2 to pi. So we want to look at that physically. This is pi over 2 right here, and we're trying to find the area under the curve of all this business here. Okay? And so the thing that we don't know, because of the fact that we have a vertical asymptote at x equals pi for secant, is are we actually going to be able to figure out what that actual area is that I've drawn in? Okay. So to do this, of course, since our discontinuity here is at the upper limit, we need to rewrite this improper integral as the limit as t approaches the upper limit from the left of the definite integral of cosecant from pi over 2 to this general value t. And here I have this asterisk here for the antiderivative of secant because you may or may not have seen this before as far as figuring out what the antiderivative of this is. There's a couple of different ways you can do it. I would say that the most easiest way to understand, but it's a longer way, is going to be the doing partial fraction expansion. There is another slick way of doing it, but it requires you having to have prior knowledge first of a nice, easy way to rewrite cosecant first in order to do it that way. You can check out some of my other videos on partial fraction expansion, and I address that in those videos. So anyway, so the antiderivative of secant is natural log of absolute value of the difference of secant and cotangent. And of course, we're going to evaluate that from pi over 2 to t. So in other words here, I'm going to go ahead and figure out what all of this is first in terms of t before I go evaluate the limit of this result in terms of t. Okay, so I do all the work for that, and I'm not going to go through all the gory details on that one. So once we're done with this, we see, well, this is what this actually ends up being. And now if we evaluate this from pi over 2 to pi, then it's going to be the limit of this particular result here as t approaches pi from the left. So I rewrite cosecant t minus cotangent t in terms of cosine and sine, so that it makes it a little bit easier to evaluate. So I get it into that form, and then I essentially just plug in pi wherever I see t, and we see that in this case we still end up getting a natural log of absolute value of infinity, which ends up being infinity. And since infinity is not a real number, we know that this particular improper integral will diverge. Now, what does that mean? That means here, because of the nature and how this function increases as it approaches this vertical asymptote here, the rate at which it increases is too slow for us to be able to actually figure out what the area from pi over 2 to pi in between x equals pi over 2 and the vertical asymptote will be. Okay, now if we had a function that would increase slightly faster than what cosecant does from pi over 2 to pi, then maybe we would be able to find out what that actual area is. But because it doesn't, it's too slow, that's why we can't do it. So that's how we end up getting this answer here. Okay, so for our next example here, notice that this is an improper integral because of the fact that we know that this function at x equals 0 has a discontinuity in it, because of the fact that x equals 0 here would make this whole entire integrand here undefined. Okay, so if you think about it, if I had e raised to the 1 divided by 0 over 0 cubed here, essentially you know that the exponent would be undefined, and anything divided by 0 is undefined as well. So that's where we have our problem. Okay? So in noting that, we know that this is going to be an improper integral because of the fact that our lower limit here is actually not in the domain of this particular function. Okay, so we do the same thing that we did for the previous example, is that we try to do the best that we can to evaluate it using the definition of what an improper integral is. And so here we'll say the limit as, since this is going to be the lower limit, I'll call it a this time, as a approaches 0 from the right of integral of a to 1. And I'm going to do this x raised to the negative 3 e raised to the 1 over x dx. So this is what we would need to figure out. Now, the hint that I give here is that you may want to use integration by parts here to get started. All right, so to do that, let's first rewrite this particular function here, or our particular integrand that we have here, in this way. So I'm going to erase this here. I'm just going to go ahead and try to write it all in here, but I'm going to write it in a different color. So I'm going to have limit, say approaches 0 from the right. I'm going to do this. And here what I'm going to do is I'm going to break this up like this. X raised to the minus 1 times x raised to the minus 2 times e raised to the x raised to the minus 1, all that dx. Okay? And I'm just going to rewrite this way. I'm just going to call it I. Let this definite integral here on the inside be I. Okay? So we're going to say solving I. So first thing I want you to note here is that if we do integration by parts, then we want to use this portion here to be the dv in the integration by parts, and we want this part here to be the u in the integration by parts. Okay. Now, reason being is that the dv here, if we really look at this, what we're saying that is that we want to take the antiderivative of x raised to the negative 2 times e raised to the x raised to the negative 1 dx. So that's essentially what we're saying here. Okay. Now, I look at this differently. If I go find out what v is, then I'm essentially saying what is the antiderivative of this. And of course, I could use a substitution here. Okay. So let me get a different color. So if we let u equal x raised to the negative 1, then that means that du is going to be a negative x raised to the negative 2 dx, which that's exactly what I needed. So what this tells me here is that v could just be the integral of e raised to the u, and I see here that I have a minus x raised to the negative 2 dx, so that's just going to be times a negative du. Okay, or we can just put the minus sign on the outside here and just look at it as e to the u times du inside the integral. Okay. Now, of course, in doing that, that makes life easy for us, because we know that the antiderivative of e to the u is just e to the u. So that's just going to be e to the u. And since u was x raised to the negative 1, we'll just keep it that way. Okay. So that is what our v is. For our u, we have x raised to the negative 1. So that means du is going to be a minus x raised to the negative 2 dx. Okay? And so now that we have that together, we could go ahead and say that I is just going to be u, excuse me, uv, and that will be integral of v du. And note here that because we have a definite integral, we're going to have to put our limits of integration here and also here. Okay. So our u is x raised to the negative 1, or just 1 over x. I'll write it as x raised to the negative 1 for now. And our v is going to be e raised to the x raised to the negative 1. And all that's going to be evaluated from a to 1 minus, and we do integral from a to 1 of our v is e raised to the x raised to the negative 1 switch that. And our du is just going to be times negative x raised to negative 2 dx. Okay. Now, notice here that what we need to take the antiderivative of now is essentially almost the same exact thing that we had to deal with here, minus the minus sign. Okay. So, of course, this is a multiplication sign. Here is a negative sign. And notice in here, I forgot to pull down this minus sign that is here, which means it should be there. And this also means that I should have a minus sign in here, which means I should also have one in here. Yep. So that should be a minus there, and these minuses right here. Yep. All right, so because of that, we know that this negative and that negative will turn out to be positive. Okay, so I'm going to go ahead and just erase those. And here, from what we saw below, when we did the substitution, we saw that we had this negative pop up here. So what I'm going to do to make life easy, or easier I should say, is let's go ahead and make this a plus and bring the minus in here. And from what we saw here, we know that this minus x raised to the negative 2 dx could just be replaced with du, and this e raised to the x raised to the negative 1, that could just be e to the u. Okay, and of course the result here, if I do all that, it's just going to be e raised to the u, and that's because we already have the negative part kind of wrapped up into all of this. So we know that du is just going to cover all of this. The u is going to cover all of that. So essentially here this just ends up being e raised to the u, and we're going to evaluate that from u of a to u of 1. And I'm saying u of a and u of 1 because we have to change these x values of a and 1 to being in terms of u now. Okay. And I'll go ahead and address what u of a and u of 1 are going to be in the next step. All right, so for the rest of this, I'm just going to copy it down. So this will be a negative e raised to the 1 over x, and we'll evaluate that from a to 1 plus what we got going on here. Now I'm going to do this in a different color. So my u of 1 here, of course, remember u is going to be x raised to the negative 1, or 1 over x. So this would be this basically. So that's just 1, and u of a would just be a raised to the negative 1, or 1 over a. So here I will go ahead and replace this u of a with 1 over a, and u of 1 with 1. All right. So now all we just have to do is just literally work it out and see what we get, and then we take the limit of that result. So here I'm going to plug in 1 everywhere where I see x, and then plug in a afterwards. So I'll have a minus e raised to the 1 over 1 minus a negative e, do this over 1 like that because of the 1 that goes here. Make sure I'm clear there. And then we have a minus e raised to the 1 over a, all that over a. And then your left term will just end up being a minus e. And this negative and that negative will end up being addition. And so you'll just have plus e to the 1 over a over a. And so that is all the stuff that's inside of here. All that just ends up being this expression right here. Okay. All right, so to finish this out now, so therefore, we do the limit as a approaches 0. I'm just going to copy what we had up here. A approaches 0 from the right of integral of a to 1. And that was x raised to the negative 3 times e raised to the 1 over x dx. Yeah. Pen's not acting right here. So if we do that, this is the same thing as the limit of whatever I was. And we see here that I was just, and I'm just going to do it like this, e raised to the 1 over a minus e. Okay. And we need to evaluate the limit of that as a approaches 0 from the right. And essentially just plug in 0 wherever you see a. And unfortunately, this first term here, that's going to be an undefined term, mainly because in terms of limits, we know that 1 divided by 0 would be infinity. And of course, this would be, if we keep on doing it, that would be e to the infinity would be an infinity. And of course, now you got an infinity over 0. And again, here that is indeterminate form we can't deal with. So, or you can look at the 0 over infinity, infinity over 0 as an infinity times an infinity. Okay. So, needless to say, all this just ends up approaching infinity at the end of the day. And since infinity is not a real number, then that means that this particular integral here, improper integral, it's going to end up being divergent because of this end result here. Okay, so this concludes the second video in the improper integral series of videos that I'm going to do for you. The third video is going to be one that's going to be a little shorter than some of these others. And for these, we are going to be evaluating integrals that we know, improper integrals that we know are convergent. We just kind of want to go through the process like how we did here to be able to figure out what those actual results or what the final value of that improper definite integral would be. So the next video will be on that. So I hope to see you there.